Okay, so these last 2 days of notes then really focus on one specific force. They focus on the force of gravity. You can see the topic of today's notes is universal gravitation, and tomorrow we're going to talk about gravitational field strength. I was thinking this morning as I drove in, I quite like the you guys are first thing of the day because it gives me a chance to think for half an hour as I drive from Lethbridge as to what I want to talk about. Physicists. Really what physics studies is the interplay between matter and energy. If you guys remember that from like my very first day of notes in physics, chemistry is all about how matter changes. But physics is all about how matter and energy are related to each other. Why does this matter move? Why does it matter? One of the things that physicists are trying to resolve then is a way to make sure that we can explain the everyday life objects, as well as the exceptionally large objects, as well as the exceptionally small objects. So one more time. Physicists have to be able to reconcile the math, the calculations, the understanding for everyday life objects. Will this chair fall? Will this table maintain its structural integrity? If I throw a football, how fast will it go? I mean, that's everyday life stuff. But we have to move past that. If we truly understand the laws of physics, we should be able to apply them to everything that has matter. Does that make sense? And so that means we need to be able to apply them to the very small. These rules should still apply to atoms, to subatomic particles, like protons and electrons. But it should also apply to the exceptionally large. And so today we're going to start focusing on one of the most fundamental, theorems of physics, gravity. And we're going to start talking a little bit more about how this applies to the exceptionally large. Because the math should be able to be calculable, whatever the word is. We should be able to calculate the math for not only everyday life objects, but for planets, for the universe. Gravity should hold everywhere. Does that make sense? I'm going to go to my notes here. I'm just going to write an extra slide. This is what I was thinking about this morning. If you guys eventually go far enough in physics, you may have somebody else explain to you the 4 main forces. There are 4 main forces. That, maybe I should be more specific. These are the 4 main forces that happen like naturally in the universe. Obviously, I can push a chair with a force, but that's not really what I'm referring to. I'm referring to natural forces that happen anywhere and everywhere, really without like humans kind of intervening. You know what I'm going here? And so one of them is what we're going to mention today. One of the forces that we've discovered seems to happen everywhere in the universe is gravity. We have gravity on Earth, right? But there is gravity on the moon. It's not as strong, but it still exists. There would be gravity by the sun. We'd probably die if we were that close to it, but there is still gravity there, right? We actually know this because the Earth rotates around the sun in part due to the gravity of the sun. So gravity is one of the main forces. It's what we're going to focus on right now. There are other forces that you'll learn about. I don't want to focus on them too much today, obviously. But there's another one known as the electromagnetic force. We actually cover this in Physics 30 a lot. Electromagnetic, you guys can pull the word apart. Basically, it has to do with the forces behind things that are electric or magnetic. You have 2 magnets, right? They will either oppose each other or they will stick together. Right? That is some sort of natural force that we can find in nature, not to be redundant. Does that make sense? Right? Where it's not the same thing as me pushing them together, but they have a natural tendency to either push or pull each other. Things that are positively and negatively charged have that same sort of ability, right? You guys know that negatives will attract positives, but negatives will repel other negatives. You guys have heard this before, right? That's another one of those sort of like natural forces where it's really not based on a human pushing something. It would just happen in general. Another one of the forces that you'll learn about is called the weak nuclear force. And this is a force that we also cover a little bit later in Physics 30. Weak nuclear forces really refers to things like decay, fission and fusion, if you've ever heard of these words before. where we can actually cause the nucleus of an atom to, say, fuse with another atom, or the nucleus of an atom to actually break into pieces. Maybe you've heard of things like alpha radiation or beta radiation. Or, I know this one gets used in movies and stuff like that, but this actually does exist, gamma radiation. You ever heard of that sort of stuff before? So we'll discuss this later. That's another type of force. The fourth fundamental force, we really don't actually describe all that much. In part, this is what I love about physics, because physicists don't fully get it yet. That's one of the things I love about physics, is there are a lot of questions that you could ask me, and I don't actually feel ashamed to tell you that I don't know the answer, because the smartest minds in the world don't actually know the answer. This last force is known as a strong nuclear force. They're actually kind of related. I can explain the strong nuclear force to you. I cannot explain to you why it happens though. So here's the strong nuclear force. You know how in an atom, you have a nucleus, and in that nucleus you have all sorts of protons, all sorts of positives inside the nucleus. Those are all positives. And then one of the ways that we draw an atom is that there's electrons just kind of floating around somewhere out here. According to electromagnetic forces, what should positives do to each other? They should push each other apart, right? So based on our understanding of forces, a nucleus should, by natural tendency, blow itself up, right? All those protons should not want to sit next to each other. And yet, for some reason, they do. This is one of the cool things about physics. Why? I don't know that we fully get it yet. We know there is a force keeping all of those protons tied together. We don't know why. We don't fully get it yet. Physicists are studying things like, maybe you've heard of dark matter. Ever heard of that before? Dark energy. They study things like the quantum theory. On the Big Bang Theory, if you ever watched that show, Sheldon Cooper is a string theory physicist, where he studies that sort of idea. And it's kind of cool to know that, like, we don't fully have physics figured out yet. We're still working on it. So, anyways, I digress before I get too far off topic. These are ultimately the four main forces that physicists have discovered that exist naturally in our universe. And they should apply from the littlest of atoms all the way to the largest of galaxies and solar systems. And maybe you'll hear people talk about how they want to find a unified theory, where we want to be able to reconcile both the very small and the very large. There's actually a second dimension to it. Boy, I'm getting off topic, but it's okay. This is cool stuff. Where it's not only about the very large and the very small, but also about the very slow and the very fast. Maybe you've heard about Albert Einstein's theories of relativity. You've heard that phrase before. We'll cover that at some point too. There is some different calculations when things approach the speed of light. Cool science about black holes and time travel if you could go faster than the speed of light. Again, we're still working on this stuff. I shouldn't say we. I'm not actually working on it, but physicists out there somewhere. So, anyways, back to my point. Today, we are really going to want to cover gravity in general. And if you haven't picked up on my point here, we need to be able to talk about gravity from the smallest of atoms to the biggest of solar systems. So, oh wait, let's move on. So, some history. So, I mean, we're talking way back in the time of Sir Isaac Newton, who I think I've mentioned before. He really had a goal to try to explain gravity. And so far, we have really covered his three main laws. Okay? So if I haven't beaten you to death with these, Law 1, inertia, objects stay in motion, or they don't. Law 2, the sum of all your forces, your net force is mass acceleration. Object 3, there's an equal opposite reaction. Those are his main laws of gravity. Really, what he then concluded then is gravitational force must exist between any two masses, both of them being attracted to each other. Newton's third law basically says there's an equal opposite reaction. He concluded that it's actually not gravity that's just acting in a downwards direction. He concluded that if his third law really does hold true for everything, really, it should be a double-sided arrow. Let me show you that one more time. It's not just that gravity causes the apple to go downwards, because that doesn't fit his third law, right? For every action, there should be an equal and opposite reaction. He concluded that it must be that way as well. And I think maybe I've discussed this before with you guys. We notice the apple falling due to its amount of mass compared to the Earth's mass. I know not everyone's done the quiz, but you guys remember there was a question on the quiz about two people who were pushing each other apart with a skateboard? You know what I'm talking about there? If they have a different mass, it kind of changes things. Well, when you consider the mass of the apple and the mass of the Earth, the mass of the apple is so incredibly tiny that although it does gravitationally pull on the Earth is so big it really doesn't move. Does that make sense? What we notice is the Earth being so big and the apple being so small. We notice the apple actually getting pulled towards the Earth, but really, actually, both are happening at the same time. Let me show you some more slides to talk about that whole Newton's third law idea. Here's some people swimming. I found this online. I thought this was worth looking at. When this person pushes themselves forward off of a wall for swimming, Newton's third law is in play. Because really, this person is pushing the wall. However, the wall is fairly large, fairly massive. It's kind of fixed to the ground, which is even more big and massive. So does this person really push the wall back all that much? No, not really based on its size. But the wall pushes back on the person, and therefore the person gets propelled forward. Does that make sense? Or when a person is swimming, you push the water backwards, the water pushes you forwards. Right? I mean, Newton's third law is one that we can see in all sorts of places. How do you skateboard? You push on the ground pushes back on you and propels you forward. When you push on the ground, are you really moving the Earth all that much? Well, no, because the Earth is massive, right? But if I do the exact same thing I've done before where I'm on this chair, and I do that, the chair is pretty small, right? So I can push the chair backwards and me forwards. But really the same logic happens with the Earth, it's just the Earth is so big, we don't really notice it move. Does that make sense? So that's basically what my final slide on this here is that gravity, Newton then concluded, is not a one-way force. It's actually a two-way force. We should have two arrows being drawn. We should have an arrow being drawn down saying that the Earth is pulling down a person with a force equal to their weight. Remember their weight is mass times gravity? But really, the person is actually pulling the Earth up with a force equal to their weight. It's just the Earth is so massive, it doesn't really move all that much. Does that make sense, that concept? So, some more writing here then. You guys can more or less just read this. Newton hypothesized then that any object which has mass is gravitationally attracted to every other object having a mass. And this is the gravitational force. In a way, I need you guys to start changing your mindset about gravity. You know how I showed you some of those forces, the other forces, electromagnetic, stuff like that? You need to think of gravity more like magnets. Because that's really what happens. You know how you have two magnets, right? And they'll eventually stick together. You know, there's a gap between them. You just let them go and they click together. Well, that's really what gravity does. It takes object one and object two, and it causes them to move towards each other. It's just kind of not how big they are. This kind of makes sense. The larger the masses of the objects, the larger the gravitational force. Okay. Is there gravity on the moon? Absolutely. But maybe you guys have seen pictures of people walking or doing the jumping on the moon. Really, they're more weightless because they can jump really high because the moon is nowhere near as big. And so although gravity exists, gravity on the moon, don't quote me, but I think it's about 1.62 meters per second squared. And the reason why it's so much smaller is that the moon is so much smaller. Right? I have a friend from university. He was a pretty large fellow. He was like 300 pounds. And he always would joke, you know, that he was the most attractive person in the room, gravitationally speaking. That was always his line. Right? And maybe you kind of get it. I mean, I don't want to be mean to my friend, but he's probably not, by most people's definition, the most attractive person in the room. He's a big guy, but, I mean, he is kind of right by that, right? Because he has the largest mass, he therefore is exerting the most gravity of everybody in the room. I mean, it's not really that much in comparison, but I found this slide here to try to illustrate the idea here. Let's say you're holding an apple. Well, the apple and the Earth, they have an amount of gravitational force between them, right? And because the Earth is so big, you can see that there is a certain amount of gravitational force. One is positive, one is negative, because they're each going opposite directions, right? But the truth is, there's even a gravitational force between the apple and the person. Okay. But right now, there's a force of gravity between me and that table right there. I don't expect that table and me to start just merging together and to have the two of us just kind of falling together, because neither of us has really that much of a mass. Does that make sense? In the grand scheme of things, when you start considering the very little to the very large, what we consider to be our everyday life-size objects in the big picture is actually really not all that big, because we're not the size of a planet. Does that make sense? And when you start thinking about how big the universe is and how many planets and solar systems and galaxies and universe and stuff, right, we're actually relatively insignificant, aren't we? Right? And so therefore, the amount of force between me and an apple is not, there isn't any. I mean, there is, but it's how many zeros is in front of this number, right? But if you start talking about things between planets, well, now there's enough of a force to actually notice it. You know what I'm saying here? If you would like to talk with me later about something like basis for how the early universe happened, I'd love to share more thoughts on you, but that's actually one of the ideas behind how the universe was formed, is that all of the matter that would have existed after the Big Bang Theory, there was all sorts of atoms of like protons and helium and hydrogen, and they slowly but surely, due to gravity, would have eventually been attracted to each other, then forming larger clumps of matter. But if you want to talk more about that, come talk to me later. Let's move on. There is one more thing that matters as well, and it's distance. It's not just mass, but distance. I want you to think back of the magnet example. If I have two magnets that are this far apart and I let them go, they may not suck themselves together using magnetic force because they're just too far. Does that make sense? So the distance between them also kind of matters as well. The closer they are to each other, the more that gravity takes place. And we actually kind of know this when it comes to things like space travel. The further up a spaceship gets in terms of its altitude, the less gravity takes hold, until eventually they get to a point where pretty much gravity doesn't really take hold very much at all. And there's that weightlessness in outer space, hence the picture here, right? Where they actually have to simulate gravity sometimes because people have no ability to orientate themselves when they're free floating on a spaceship. Does that make sense? Right? Is there still gravitational force of attraction between the Earth and the spaceship? Well, yeah, but kind of similar to me and the apple, because the distance is now so far, the amount of force is also pretty negligible. So there's actually two main things you have to consider then. Mass, the mass of the objects you're talking about, and distance, the distance between the objects. Those are the two main factors. I'll write that up. Mass and distance. It's actually a relationship that we can graph. And for you guys in my grade 12 class who've done math last year, maybe you'll recognize this sort of graph. You guys were doing it in about 2 weeks. So we're just right behind the math concepts. Do you guys remember what we call a graph that looks like this? Reciprocal. Good job. Yeah, this is a reciprocal graph. Sometimes we'll use the word inverse. Both would kind of, they actually in math, they mean different things. And in science, they mean the same thing. Sometimes when we choose language with which to describe things in science, it doesn't make a lot of sense. Because in math, an inverse and a reciprocal are different, but in science, they usually mean the same thing. This is the sort of thing like, I think I've actually shown you this before. It's like a seesaw. When one goes up, the other goes down. That makes sense? So when the amount of distance goes up, the amount of force goes down. When the amount of distance goes down, the amount of force goes up. Does that make sense? There's also a direct relationship then between gravity and mass. So I think I've shown you this symbol before, this little alpha symbol. Do you guys remember, did I tell you this before? What that little symbol here means? It means proportional to. You ever see this symbol somewhere, this little alpha symbol in a formula? It means proportional to. So this means that the force of gravity is directly proportional to the masses of the object. Essentially what I'm saying here is that if you want to up the force of gravity, up the masses. If you have heavier objects, you'll get more gravity. Does that make sense? So that's a direct relationship. One goes up, the other goes up. Here, the way it's proportional is it's an inverse relationship, where if the radius, we're using radius as like distance in this one, by the way. R stands for radius, but radius is a distance. Okay. If you were to up the radius, what would happen to this fraction if this number got bigger? The fraction then would get smaller. Does that make sense? So if you were to up this radius, the force of gravity would actually go down. So that's known as your inverse or reciprocal relationship. So this symbol here just refers to how they're proportional to each other. Long story short, I've finally gotten around to my point for the day. Here it is. We have a new formula. Yay! So after all of that preamble, here's our new formula. And this is known as the universal gravitational formula. For the most part, you guys have been allowed to just use mass times gravity, which works if we're talking about things on Earth. If we're talking about things on Earth that are relatively the same distance apart. But what happens if we want to find the amount of gravitational attraction between someone on Mars? What if we want to find the amount of gravitational attraction between your pencil and the eraser on the end of it? I know that's a silly question, but there is a force of gravity, right? And this is the fundamental problem for physicists, is that although we can do everyday life type stuff, we should, in theory, be able to do it from small to the large. You know what I'm saying here? Hence the need for the universal gravitational formula. So here's how it works. F right here is the force of gravity. Pretty straightforward. It's dependent on 3 variables and a constant. One of the variables is mass 1, whichever object we're talking about. But really, gravity always takes place between 2 objects, hence the need for having a second mass. So you always need to know the mass of both objects in which gravity is actually having an interplay between. R, we write R for like radius, almost as though it's like a part of a circle. It'll make more sense maybe once we do circular motion, but maybe think of like how here's the Earth, and then the moon goes around the Earth. And you know how the moon goes around the Earth in like a circular pattern? Maybe you can see now that the distance between it, in a way, is kind of like the radius of a circle. So we use R in this formula, but R is really a distance. There's one more thing though, and you're going to discover that these crop up a lot more and more as we go into physics. Although force is proportional to mass and inversely proportional to a radius squared, it actually doesn't fit perfectly unless we use what's called a constant. And there are a lot of formulas that require a constant. So much so that if you guys actually have your formula sheets nearby, I'd like to point out some of the many constants we're going to use over the next little while. So let me see so I can find a formula sheet to look at. So there's a whole section in your data book . You guys find this section here, which talks about some of the constants that you may need to use as we go through. We've actually talked about a couple of them already. The acceleration of gravity near Earth is 9.81. Again, that's the whole point of today's lesson, though. What if we're not on Earth? What if we're somewhere else in the universe? There are so many other constants we may need to use here, like eventually we'll get to elementary charges and refraction of air and speed of light and Planck's constants. But for right now, I want to focus on Newton's gravitational constant, which is 6.67 times 10 to the minus 11 Newton meters squared over kilogram squared. At least for right now. Can you guys see that one right there? I know it's kind of blurry on mine. You give me a funny look. Are you okay?
Yeah, I was looking for Newton's gravitational.
Oh, sorry, I didn't call it Newton's gravity, but it's the gravitational constant. Yeah. So here it is right there. If it's okay with you guys, I'd like to start by just doing some examples using it. and then I'll show you how we actually found it, if that's okay. Because I think we just need some practice using the formula first. So, but I will explain where the heck it came from. So, again, here's another slide, just kind of talking about the same concept. You've got two different masses with a distance between them. We've discovered that there is a constant here. You don't really have to memorize it because it's on your data sheet. That being said, the more you do it, you probably will actually memorize it by the time we're done, because you'll use it. So right here, I actually explained for a little bit how it was discovered, but I feel like I should put this at my end of my notes. So I'm going to skip the part on the Cavendish experiment, which talks about how we discovered G. And I want to go back a little bit here, and I just want to, let's just assume that we can work with it. Let's do some questions, then we'll go back. So this leads me to one of the, in my opinion, most revolutionary discoveries in physics. We can now calculate the mass of the Earth, which maybe seems a little silly because it's like, well, how do we mass everything else in the world? We put it on a scale, right? If I want to know how heavy I am, I go stand on a scale. We can't do that with the Earth. Because the Earth can't go on a scale, obviously, right? But, again, therein lies the issue, right? If physics really truly is universal, we should be able to go from the very small to the very large. Earth clearly has a mass, right? We should be able to calculate it. And so this was brilliant, whoever came up with this. They put two formulas together. They said, well, the force of gravity, we've learned, is equal to mass times gravity. That is a formula that we've been working with for so long. Now, it normally applies to things that are of regular everyday size, right? But it should still work. But Newton's formula, the universal gravitational formula, says that gravity could also alternatively be calculated using capital G, m1, m2, over r squared. So far, so good? So we have two formulas for gravity. One, which we've been using all along, but this one, which was developed. Trust me, it works. Would it not make sense then to say that they actually should equal each other? All right, now, I've got a bit of an issue here, and I've been hopefully guiding you guys in terms of doing a good job of your notation, because it's so important to keep track. Because really, I have a mass right here, I have another mass right here, and I have a third mass right here. So it'd be good to actually maybe notate them a little better than just M, M1, and M2.
Breakfast.
Yes. Do you want to say something? I will. Yes, thank you guys. Okay, so I want to notate these masses a little bit better than just what I've got sitting there. So let's talk about the, sometimes I'll refer to these, by the way, as the little gravity formula and the big gravity formula, because they both do calculate gravity, just one is little and one is big. Right? So when we use the little formula, what is the mass of? Well, it's the mass of whatever object we're talking about, right? If it's a box sitting on an inclined plane, it's the mass of a box. So, I mean, just for the sake of argument here, why don't we just call this the mass of, say, a box? Okay. Now, why does that box fall towards the ground? Well, because the box pulls the Earth up, and the Earth pulls the box down. So over here, when I've got to label my two masses, in a way, one of the masses better be that box, but the other mass better be the mass of Earth. Now, I don't care whether it's a box or a pencil or whatever object we have, but what I'm hoping you'll see here is that the mass that goes in this formula here is the exact same mass as one of the two masses that goes in this formula here. One of them is the same, the other one has to be the mass of the Earth. Here's what's really cool here. It doesn't actually matter what that mass of the item is here because it's on both sides of the equation. Mathematically, it cancels. And it creates a new formula. G equals big G times the mass of the Earth by the radius squared. we now have a formula that could be used if we have the rest of the information to help us find the mass of the Earth. So let's do some algebra next then to rearrange to get mass of Earth by itself. To do that, you'd have to swing up the r squared and divide by g. So if we took g times by r squared and divided by the big G, we would now have a formula to find us the mass of the Earth. Okay, well, experimentally, we've determined little g to be 9.81 because physicists were just able to, over time, recognize how fast things fell, right? Essentially, g is an acceleration, right? The acceleration due to gravity, and it has been calculated numerous times by finding a velocity initial, a distance, a time, a velocity final, and we are fairly comfortable in saying that this g value right here is 9.81 meters per second. Because we've experimented so many times, we know what acceleration due to gravity on Earth seems to be. Now we need to know the radius. Yeah, where'd you get that from, though? It's one of the constants there. Can you elaborate, though, as to what constant it was? Yeah. One of the things that's also on here is the radius of the Earth. Yeah, now granted, the mass of Earth is right below it, but hopefully we're going to actually prove that number is there. Okay. But here's the proof for it. We actually using, and if you want the proof, I can show you later how we calculated the radius of the Earth. It was pretty clever as well. But the radius of the Earth is something that mathematicians and physicists have known for a while. So if the radius of the Earth is 37 or 38? 37 times 10 to the 6. Okay, I need to point out that whole number needs to get squared though. Don't forget to square the whole thing. And then we have to divide by the gravitational constant, which I know I haven't explained how we got it yet, but if we could just go with the fact that, I promise you it's been done correctly, let's see if we can get that mass of the Earth. So this was 6.67 times 10 to the minus 11 newtons kilograms squared over meter squared. Meter squared over kilogram squared. Flip that then, I bet. I haven't done this in a while. Let's grab a calculator and let's see whether we get what the accepted mass of the Earth happens to be. So, from the top, 9.81 is a fairly accepted value for gravity on Earth. We can experimentally determine that. We're going to times by the radius of the Earth. I'm going to put the bracket around this. I'm going to go 6.37 times 10 to the power of 6, and then square that. And then I'm going to divide by another bracket of 6.67 times 10 to the power of negative 11. And hopefully you get more or less what I have here. 5.9679 times 10 to the 24. You guys get that as well? How does that compare to the accepted mass of the Earth? That's pretty close. 5.97 times 10 to the 24. 5.97 times 10 to the 24. This is brilliant, honestly. Whoever thought of this, because we now had a way to determine the mass of the Earth. We know the Earth must have a mass, right? We can't put it on a scale, right? But we actually have a way of calculating it. It's kind of brilliant. All it needs then is 3 requirements. The requirements were, you have to know gravity on Earth. You just do a bunch of experiments, right? Really, gravity is acceleration. To find an acceleration, we could just drop an object with an initial velocity of nothing. We could find its distance, we could find its time, and we could eventually confirm what gravity is, just using basic kinematics. The radius of the Earth was found years and years ago using ancient mathematicians. I'll show you a proof if you care. Let's talk about now about g then. So I want to go back to the slides I skipped. Let's talk about how we calculated that gravitational constant. So the guy who figured this out, his name was Henry Cavendish. And his experiment is quite brilliant in my opinion. So I've got a whole bunch of writing here. I'll read it off later if you guys want to, but here's the idea. What he did is he put 2 fairly large masses. I'm assuming they were like lead or something, very, very dense. 2 of them right here. And they were fixed. This should be in like a fixed location. They are bolted to the floor or something. And then what he does is he puts a rod hanging from, say, the ceiling. And it has the ability to rotate, if you can kind of picture this. Right? And on the end of this rod, he puts two masses. And he puts them fairly close. Now, granted, this diagram here is probably not to scale, right? But he puts them fairly close to each other so that this mass right here and this mass right here are close enough that gravity might actually matter now. And what ends up happening is, well, this one's fixed and this one's fixed. So it's really not allowed to move. Does that make sense? But because this one's hanging from a wire, this one here is allowed to move towards that one. Kind of like how you move towards the Earth. The Earth tries to move towards you, but it's really so heavy it doesn't, we don't notice it, right? But the same thing happens on this side here. And this small mass now gets attracted gravitationally to that one there. And the way that he determines how much it moves is based on this wire right here. As the wire twists, he then measures the twists of the wire to figure out how much force there is. Does that make sense? Working backwards then, he knows all of the information. Because he knows how this formula is supposed to work. He knows this formula is this. If he can find the torque on the wire, he can relate that to a force. He will then go back and weigh the masses on a scale, and he will determine the distance they were apart from each other when he begins, and he actually just mathematically worked backwards to solve for this g value. That makes sense? It's actually quite brilliant. Nowadays, we actually use lasers and mirrors. So you can even kind of see on this picture right here, maybe what they do is they attach a mirror to this here, and as the mirror twists ever so slightly due to the torque, if we send a laser onto the mirror, the laser would, I have a better picture actually. Let me find a better picture. Not this one, this one. So this might be what we do nowadays. Hopefully you can kind of see the exact same sort of setup here. You've got two masses that are more or less maybe fixed. You've got these smaller masses right here, and eventually they're going to be attracted to each other, right? And what will happen is it'll twist just a little bit. But if we use a laser and a mirror, we would be able to detect that motion, because normally there's a laser that goes off the mirror and bounces over to here. But if you twist that mirror just a little bit, the laser would then cause it to bounce to right there instead. And then we can use some math and mathematically calculate backwards, just how much twisting the wire had. And then by knowing how much twisting the wire had, we can maybe relate it to how much force the wire had. And then again, once we have force, we can just go weigh the masses. We'll know the distance because we can measure that. And we can work backwards and solve for gravity, or the gravitational constant. That makes sense? So that's the Cavendish experiment. If I were to put together like my top 10 list of important scientific contributions, just in general, this would be on the top 10 list, without a doubt. Because it's enabled us to do so many things once we have the gravitational constant. If we didn't have that capital G constant, we wouldn't be able to do almost anything that involves outer space stuff. Because we need to be able to calculate the mass of Jupiter in order to send a plane to Jupiter. Can we put Jupiter on a scale? Well, no, obviously not. But we now know how much gravity there will be on Jupiter because we can calculate its mass. Indirectly, obviously. Does that make sense? So this was actually really, really important to just society and physics in general. Okay, so let's do some more examples. Let's say that you're at Mount Logan, which is the tallest mountain in Canada. It's 59 meters above sea level. You guys probably are aware of this, but like the further up you go in terms of height on a mountain, there's a couple of things that change. For you guys who took chemistry, we actually talked about this in the gases unit. There is less atmosphere, which means it's harder to breathe. Why is there less atmosphere on the top of Mount Logan? Because there's less gravity. And really, what keeps all of these air molecules nearby conveniently for us to breathe is gravity. Right? Gravity takes place everywhere. It should be universal, right? So the oxygen that you are breathing in, be thankful for gravity to keep those oxygen molecules nearby, because if not, and they were allowed to roam everywhere, we might not be able to breathe. Does that make sense? Earth is very unique. It has just the right amount of gravity to maintain an atmosphere, but the higher up in altitude you go, the distance increases. If the distance increases, Unfortunately, the amount of force decreases. There's less gravity, therefore there's less atmosphere on the top of the mountain. So therefore, sometimes people who climb Mount Everest, is that hear this, they have to bring oxygen tanks with them because it's hard for them to continue to breathe on top of the mountain. That wasn't actually my point. My point is that we want to calculate how much gravity there is at the top of Mount Logan because it should be less. So we're going to see what the weight of a 5.50 kilogram person should be at the top of the mountain. And I bolded this because some people might say, isn't his weight 55 kilograms? That's his mass. We use those words wrong in everyday life. Again, if I could go back and change vocabulary, there's a whole bunch of things I do in the sciences because sometimes we started using a word and then it's since been used incorrectly and now it's kind of hard to change. Does that make sense? So, but this is a mass. His weight would be how much gravity affects him. So we're going to use the formula. The force of gravity, which is essentially his weight, will be capital G, m1, m2 over r squared. Our new formula. Let's start plugging in the values in it. Thanks to Henry Cavendish and many physicists who came behind him to confirm, we now know this gravitational constant. It's 6.67 times 10 to the minus 11. What is it? Kilograms. Nope. Oh, I haven't done this in a year. 11 newtons meters squared over kilograms. I'm going to do it backwards though. I'm going to write this down. Okay. Okay, we need to know mass 1. Well, I know one of the masses is the person himself, right? So that's 55 kilograms. What's the other mass? Earth? Yeah. I don't have a lot of room here. So I'll just put mass of Earth 5.97 times 10 to the 24 kilograms. I want to focus on units right now. Do you see how the constant here has kilograms squared on the bottom? Hopefully you can kind of see why it has to have kilograms squared on the bottom, because 1 and 1 will cancel at both of those. Then on the bottom of the fraction, we need to know the radius. Well, the radius of the Earth has been calculated to sea level. So that, what was it again, 6.37 number? It's calculated to sea level, but you're on top of a mountain. So our radius is going to be a little bit bigger. So what we have to do is this. We have to do the radius of the Earth, 6.37 times 10 to the 6 meters. That's the radius of the Earth. But we have to add on the fact that we're on top of a mountain. So I'm doing this here. Because when you're on top of a mountain, you're just a little bit further away from the center of the Earth. It's not a lot, but it's going to be enough to change the force of gravity just ever so slightly. Don't forget to put all of that in brackets and then still square it though. Don't forget to square it. A lot of kids, they forget the squared symbol right here. And obviously they get it wrong. So break out trusty Mr. Calculator. 6.67 times 10 to the power of negative 11 times by his mass of 55 times by 5.97 times 10 to the power of 24. Enter. Divide by bracket 6.37 times 10 to the power of 6. There's the radius of the Earth. Add on the extra height from Mount Logan and square it. Let me know if you don't get this. You guys able to calculate that? Okay, what units are left? So you have already canceled out your kilograms? There's a meter squared, but isn't that meter squared going to essentially cancel this meters that are squared here? This is a force. This is the force of gravitational attraction between you, a person on Mount Everest, and, on Mount Logan, and the Earth. So we'd have to call this 539 newtons. That would be your quote-unquote weight. I know I didn't ask this in the question, but what I'm going to do real quick here is I'm going to say that's supposed to be equal to the force of gravity, right? You know how the force of gravity is sometimes written as m times g? I'm going to divide by his mass real quick. If I divide by 55 kilograms, this would give you how much gravity is on top of Mount Logan. If you divide by 55, so I get 9.795. That actually should make a little bit of sense here, because isn't gravity normally accepted to be 9.81? If you're on top of Mount Logan, gravity is just a little bit less because you're so high up that the distance between you and the Earth is just a little bit greater. You guys able to follow that last calculation I did there? Ultimately, we were supposed to stop here. I just wanted to prove how this would make sense. If that is our weight is the force of gravity, which is mass times gravity, that formula still does apply. If you then divide by the mass, I end up getting gravity to be 9 point, well, let's call it 80, but it's a little less than 9.81. The further up in altitude you go, gravity gets less and less and less, right? Until you're on a spaceship in outer space, and now there really is no gravity at that point, because it's down to like 0.00001 newtons, just like the amount of gravity between me and my sweater. There is still some, it's just almost irrelevant. Does that make sense? Let's do some more examples. So here's a slide that talks about those interplay of vocabulary. I mean, not that it's the end of the world in everyday life. You don't have to be like, say, Sheldon Cooper off Big Bang Theory and correct all your friends when they say things wrong. But you don't weigh yourself, technically. You mass yourself. It just sounds so funny to say it like that. But mass is actually your kilograms amount, whereas weight is based on the force of gravity. Okay, let's do a more typical example of what I'm going to ask you to do then. I don't think this is actually that much harder. Actually, I think it's probably way easier than what we've been doing up to now. This is usually the easier part of the section here. But now we're going to work with like intergalactic objects, because again, the math should hold for things like planets and spaceships, as well as atoms. Right? So here's an example. We've got Jupiter, and Jupiter has a bunch of moons, one of which is called, I think it's pronounced Io. And so let's say that the Sun, Jupiter, and the moon Io all end up lining up all together. Let's calculate the net force acting on it. So, to calculate force, really we have to do this twice. There's the force of gravity due to Jupiter and Io together. And then there's also the force of gravity due to the Sun and Io together. We're going to find those two forces, and when we're done, we're just going to subtract them. Does that make sense? It's like a tug of war. Io is getting pulled by Jupiter, and Io is getting pulled by the Sun. Who's going to win this fight? Jupiter or the Sun? Why Jupiter? You're right. Yeah, although the Sun is massive, it is a long, long, long ways away. Does that make sense? So, you have all the distance you need here. Right? And so what you just need to be comfortable doing is working with large numbers in your calculator. So let's write it out here. I'm going to do this for the force of gravity between the Sun and Io. So that's going to need to have 6.67 times 10 to the minus 11. I don't have enough room to write this here. Let me put this down somewhere lower. Alright, and although I do want you guys to write units a lot, I mean, I'll understand if after a while here, it's getting kind of tricky to always be writing the units in here, so I'm going to skip them right now. But when we're done, though, don't forget them. That's important. So, oh yeah, we need the mass of one of the objects. Well, they're all sitting right here. So Io is 8.93 times 10 to the 22. The Sun itself is 1.99 times 10 to the 30. And we'll divide by the distance between them. So from Io to the Sun is 7.98 times 10 to the 11. And don't forget to square that. I all of a sudden made a fundamental shift in how I wrote this last example here. You guys probably most of the time have been writing times 10 to the power of. and not that that's wrong, but sometimes it's more efficient, good reason to use the letter E, to just write an E instead. Do you guys know that your calculator actually has an E button? You haven't seen this before? E just means the times 10 to the power of. Not that it's a huge difference, but, oh goodness, where is this dog here? Here it is. It's right above the comma, I believe. It's that one right there. You see that? Mine actually has two E's for some reason. I don't actually know for what reason that is, but this is an E. You guys find that? So you may find this useful just for efficiency's sake, because now you could write it like this: 6.67 E negative 11 times 8.98 E 22 times 1.99 E 30 divided by big bracket here, 7.98 E 11 square root of it. You may find that more convenient than always typing times 10 to the power of. Before I press enter to calculate this value, I just want to point out how your calculator interprets this. Your calculator ranks this E as like the highest thing on the BEDMAS scale. So it will always do the 6.67 times 10 to the minus 11. And then after it's done doing that calculation, then it will times by 8.98. So you don't have to worry about it like taking the minus 11 and timesing it by the 8.98, because that's not how your calculator interprets it. So, anyways, this.
What did it say?
I have 1.87 to the 19.
1.86.
Did I mistype something?
Yeah, you used 9.8 instead of 9.3.
Where is that?
8.9.
Ah, right here. I screwed this one up. Thank you. Okay. If you guys don't have a fancy calculator that can go back up, do you guys know how to re-pull a line of work back up so you can just make one subtle change? This is where it's showing you. Press second, enter, and it's going to re-bring up the last line of work you did. You may find this very useful if you've got an older calculator like yours or yours as well, because then you don't have to retype the whole blooming thing for one mistake, because now all you can do is just go back up and pick out the one thing you did wrong and change that there. There, is this what everybody else got now? 1.86 times 7 to the 19? Is that useful?
Yeah.
Because otherwise you have to like literally retype the entire stupid thing, right? So one more time if you didn't catch that. To change that, go second, enter. It'll re-bring up the last line of work, and then you can go just make one little tweak. So actually, I'm going to find that really useful when I do the next calculation here. Because what are the only numbers that change? It's still going to have the same constant, right? It still is going to have Io's mass, which was this one here. But rather than it being the sun, now we have to change it to Jupiter. And rather than it being that distance, we just have to change the distance. See what I'm saying here? So this could be useful. I could just go second entry. And I'm just going to go up and I'm just going to change just a few numbers that matter. Rather than it being the sun's mass, now I'll change it to Jupiter's mass. So 1.90 times 10 to the 27. And rather than it being the distance from Io to the sun, now it's the distance from Jupiter to the sun, which is 4.22 times 10 to the 8. So that's kind of a little clever way to save myself some time in my calculator. I don't have to retype it all again. You guys able to get what I got there? still use 6.67 because that's the gravitational constant. We still use Io's mass, which I hope it is right, was the 8.93 number. Why do I put an 8? My 3 looks like an 8 there, doesn't it? Rather than using the sun's mass, though, now use Jupiter's mass, and rather than using the sun to Io distance, use Jupiter Io distance. Okay, last thought. We now need to take these two numbers and do what with them? Subtract them, yeah. So I need to essentially take my answer and subtract, and then for people who have an old-fashioned calculator, this might be a nifty trick here. So like Michael, what you could do is go like open up a bracket. So what I'm going to do is I'm going to take my last answer, then I'm going to subtract, but you know how I don't have the ability to go back up and pull that answer on a calculator? Yeah. If I do this, watch this, I'm going to go second entry. It's going to pull up the very, very last thing I did. If I press second entry a second time, it'll pull up the answer before that. Oh, it's not in the middle of the line of work though, is it? I gotta check this. Never mind. Sorry, that won't work. If you continue to press second entry over and over and over again, what it'll do is it'll go back up and find the previous line of work above it. I thought you could put it actually into an equation, but apparently not. So I guess you're gonna want to save that number with like alpha A or something like that. You know what I mean? So, anyways, long story short, I know you can't see them on my calculator anymore, but one of them is times 10 to the 22, one of them is times 10 to the 19. I don't think I'm going to be able to show this on my screen all that effectively, but when you guys subtract them, my guess is that it hardly made a difference, right? The reason being is that this is times 10 to the 22, this is 10 to the 19. They differ by so much that although there is a tremendous amount of gravitational force between the planet, between the moon and the sun, because they're so massive, because of the proximity to Jupiter, Jupiter has way more gravity. So when you subtract these two numbers, it probably doesn't even matter all that much. Does it matter? You can change one sig there? Okay. Okay. So this is the sort of thing I need you guys to be able to do now. I don't know that it's overly hard. The biggest struggles you'll have are the large capacity of the numbers. We're now working with such large values that you just need to know how to use your calculator. So I think I have one last example. But I think you guys can probably handle this on your own. Let's just talk through how you solve it. I'm giving you the mass of the moon. I'm giving you the radius of the moon. I'm giving you the mass of the Earth and the radius of the Earth. The second two you already have in the data sheet. Sorry. If I wanted you to calculate the gravitational force of a person on the moon, you would use big G, which you have. You'd use the mass of the person, 100 kilograms. You'd use the mass of the moon. Well, you have that. I gave it to you in the preamble. And you divide by the radius squared, which again you have. Does that make sense? So like, in terms of this formula, all of the information you need, you have, right? To find the gravitational force, you'd need big G. You always have that, right? You'd need mass 1. Well, there, you have one of the masses, right? You would need mass 2. Well, look, you have the mass of the moon, right? You then need to divide by the radius squared. Well, we have the radius. Does that make sense? So at some point, honestly, it's not really all that challenging. From like a puzzle perspective, it's just more challenging from a don't screw up your calculator perspective. Because you can see how that could be an issue. Do it once for the moon, do it once for Earth, and then why are they going to be different? Because the Earth is way bigger than the moon, right? Size-wise. I mean, the radius is also a little bit different as well, but it's actually similar. This is 1.74 to the 6. This is 6.38 to the 6. They're at least both to the 6, right? Whereas when you compare the masses of these things, see how this one is to the 22, and this one is to the 24? To the power of 24 is considerably larger than to the power of 22. So, therefore, the Earth is way bigger than the Moon. So there's more gravity on Earth. There's even more gravity on Jupiter or Saturn, to the point where, like, I'm actually not sure the human body could actually live on those planets because there'd be too much gravity. We would just get crushed. Like, it would actually collapse our bones themselves. they wouldn't be able to withstand that much force. It would be like, I don't know, imagine that you like fall from a really big height and you try to land on your feet and you like crack the bones in your legs just due to landing like that. By purely just being on Jupiter, that same thing would happen. Does that make sense? Just because that's how big the planet is. You would get like physically crushed into the planet. So there are certain planets, therefore, that if we eventually want to consider space exploration, are just not possible because they have too much or too little gravity for us to exist on. So that's one consideration. Now I'd like to mention things like water, air, the ability to grow stuff, and all that stuff. So, okay. I digress. I'm running out of time. You guys have any questions?
What if digressing?
I'm gonna stop going on this thing, this tangent here, and come back to the main point. I get distracted. Hopefully you learn stuff. Okay. You guys are good? Okay. Tomorrow we have one more formula to cover. It's really not all that much. So the big change, I guess, today is, like I've been, hopefully I made my point very well over the course of the class. I need you to be able to do this for the very large and the very small. I actually have a couple of test questions where I'm going to ask you to calculate the amount of gravity between like an electron and a proton. Because we can calculate that. There is gravity between the molecules in your body. It's pretty small though because of the small masses. Okay.